So we would be waiting for 2-3 more minutes so the students,
Oh, yeah,
other
no
students, they
problem,
could
ma'am.
join.
Just tell me. I have joined because I don't want to face any technical issues later on.
Yes, sir.
So please have sufficient time and let me know.
Yes, yes.
हेलो सर, नमस्ते।
Good morning, everyone. I think students would be joining. They are joining, and they will be joined. The others may be joining in next 5 or 10 minutes. So let us start on with the session for today. Dr. Vinod.
Yes, ma'am. You please continue.
A very warm welcome to Dr. Vinod Kumar from JC Bose University of Science and Technology, YMCA, Faridabad. I also welcome our principal, sir, Dr. Rajiv Sharma, who is from who is from chemistry background also. And today, the topic which uh, Dr. Vinod is acquainting us with is fluorescence spectroscopy and its application. Spectroscopy, as students, that is mainly it is about the interaction between the matter and the electromagnetic radiation. Okay, and it is not confined to a single field. It has a wide applications in sciences. And Dr. Vinod, he would be sharing his pool of knowledge with us today. I welcome you, sir, for today. And I request Dr. Rajiv Sharma, our principal, sir, um, to propose the welcome note for Dr.
Yes.
Vinod.
So, am I audible?
Yes, sir.
Yes. Madam Mitu, Head Department of Chemistry, other faculty members, and dear students. Uh, First, I would like to welcome our today's resource person, Dr. Vinod Kumar, from Chemistry Department, JC Bose, University of Science and Technology from Faridabad. And I am very thankful to him that he has spared his valuable time for students of DAV College Bathinda. Students, as Madam says, that being a chemistry student, I must say that spectroscopy is very, very important for the chemistry students. As you know, it is basically the interaction of electromagnetic radiation with the chemical compounds. And another thing, whenever you are talking about your syllabi, in that you might have gone through that structure elucidation with the help of different type of spectroscopy techniques. But importantly, uh, today's resource person is um, uh, uh, explaining the basics of fluorescence spectroscopy and its application. And you are, I think, students are very lucky that chemistry department is organizing a lecture from JC Bose University of Science and Technology. Without wasting any time, I once again welcome our today's resource person, Dr. Vinod Kumar. Now, sir,
Um,
yes,
Thank you,
thank
sir.
you.
Thank you. I would like to request Dr. Pooja Rani from Department of Chemistry, Postgraduate Department of Chemistry, DAV College, Bathinda, to formally introduce Dr. Vinod Sharma to the audience.
Thank you, ma'am. Good morning, everyone. It's a great pleasure for me to introduce our resource person for today, Dr. Vinod Kumar, who would be sharing his knowledge about fluorescence spectroscopy and its applications. Dr. Vinod Kumar has earned his PhD degree in physical chemistry from IIT Delhi and is currently working in Department of Chemistry, JC Bose, University of Science and Technology, YNCA, Faridabad. His research interest focuses on utilizing optical spectroscopic techniques, photophysical processes, chemosensors, and advanced fluorescence spectroscopy for the characterization of complex fluidic systems. His understanding of complex fluid systems, solvation, and aggregation is largely unexplored. His work aims to investigate the role of different solvents, in particular, in general, and ionic liquids in particular, in controlling aggregation. During his research career, he has published several research articles in international journals with good impact factor. He also has a patent to his credit on method for preparation of highly fluorescent biocompatible sulfur dot graphene quantum dots for bioinformatics applications. So possible to mention his each and every single accomplishment because they are a lot. His achievements have been recognized by many different awards and fellowships, including National Science Foundation Award, for publishing research paper in high impact factor journal during 2009-10 and 10 and 11. He holds international publications with good impact factor of total 75 with an average impact factor of 4.74. However, today we are here to learn an interesting application of chemistry. Thank you so much, sir, for bestowing us with your own presence through this webinar. Now I will turn the session over to Dr. Vinod Kumar. Please welcome, sir.
Thank you very much, ma'am, for the kind introduction. Am I audible?
Yes, sir.
Yes, sir.
I also welcome all the audiences on behalf of Department of Chemistry, JC Bose University of Science and Technology, YMCA Faridabad, for this webinar on fluorescence spectroscopy and its applications that is being organized by PG Department of Chemistry, DAV College, Bathinda, under DVT Star College scheme. So I also express my sincere gratitude and special thanks to the organizer for these events, especially Principal Sir Dr. Rajiv Kumar Sharma, Head of the Department and Scheme Coordinator Dr. Mitu S. Padwa, and all the members of the organizing committee. So I would like to share my screen, if you allow me. Is it visible?
Yes, sir, it's visible.
So once again, very good morning to one and all. So as I have already mentioned that today we are going to discuss a very important topic, that is fluorescence spectroscopy and its applications. So in order to create your interest in this topic, initially I would like to mention that nowadays we are very familiar with RT-PCR for COVID-19 detection, and you will be feeling very happy that today you are going to learn that topic, which is playing the essential role in RT-PCR techniques. Without fluorescence techniques, you cannot do RT-PCR. So we will also learn how this technique is playing an important role for COVID-19 detection and all these things. So before going into details, we would like to start with the basic introductory part, and after that we will jump to certain applications, including this COVID-19 detection and all these things. So as far as discussion of today's talk is concerned, so I am going to discuss with you some basics related to phenomena of fluorescence and Jablonski diagram to mention certain roots, then quantum Gill determination and fluorescence quenching, and what is the meaning of fluorescence and isotropy, and what is the difference between steady state and time resolved fluorescence. In addition to this, we will also focus on why fluorescence technique, why it is so useful, and why our focus should be on that. So after steady state fluorescence techniques, we will jump to time correlated single photon counting, that is TCS-PC technique. And then we will try to explain this RT-PCR technique for COVID-19 disease testing by making use of fluorescence. So let us have an overview of this fluorescence spectroscopy. So you can apply this technique to a variety of problems in chemical as well as in biological sciences. So biological sciences, I have already mentioned that in COVID-19 detection, RT-PCR techniques is utilizing. But in addition to this, fluorescence measurements, they can provide very good information over a wide range of molecular processes, because being a chemist, we are interested in certain molecular processes that happens. So sometimes we have to study interaction of our solvent molecule with fluorophores. So here I would like to mention fluorophore is nothing but it is the compound whose fluorescence we are going to monitor. So any compound who emit from excited singlet state, we will be calling it as fluorophore. So in case you have an interest to study the interaction of solvent molecule with the fluorophore, definitely this fluorescence technique is going to help you. Sometimes some people are in the study of particular decrease of certain molecules. Sometimes we have to report the distance between biomolecules. So in order to measure the distance between certain biomolecules, we have to make use of Froster techniques. That is also based on fluorescence measurement. And some conformational changes take place environment of these conformational changes. For example, if you are working on these and protein folding, defolding, all these things, you can study with help of this technique. And if some typing, then you can these binding interactions with help of fluorescence techniques. So conclusion is that technique can have a variety of ways, and it depends on the choice of the person and choice of the study. So let us start with the introduction of this phenomena. So emission capacity of a molecule, it can be in terms of fluorescence, it can be in terms of phosphorescence. So luminescence is nothing but it is the emission of light that takes place from any substance, and this emission of light takes place whenever the jumping of the molecule takes place from electronically excited state to ground state. So depending on the nature of the electronically excited state, we can have two type of electronically excited state, means singlet and triplet. We can classify this luminescence phenomena into two categories. One is known as fluorescence, another is known as phosphorescence. So depending on the nature of the excited state, the phenomena of phosphorescence is the emission of light from the triplet excited state. Means if the molecule is coming back to the ground state from the triplet excited state, then we will be calling as phosphorescence. So further, when we go into the details of this nature of the triplet excited state. So in case of triplet excited state, what happens? The electron that is present in the excited orbital, so this electron is having same spin orientation when it is compared with the ground state electron. So same spin means total spin of the system will be half plus half, means total will be 1. And if multiplicity is for this spin state is concerned, so multiplicity we generally give m equal to 2s plus 1. So m comes out to be 3 because total s is 1. So 2s plus 1 total will be 3. So multiplicity of this excited state is 3. So therefore we call it as triplet excited state. Further, it also becomes important to mention here that for this transition that is happening from excited triplet state to the ground state, so for these transitions, due to the spin of the electrons that is coming back to the ground state, it is having the same spin, therefore it is forbidden in nature. So this emission is forbidden in nature, so it takes lots of time before this process is quite slow. Or we can say that it takes 10 to the power 3 to 10 to the power 2 per second transitions. Or it means that if we measure the lifetime values for these type of phenomena, means for phosphorence, then the lifetime values for phosphorence are of the order of milliseconds. Or you can say that these are nothing but phosphorence is the time delayed fluorescence. Now, we are coming back to our phenomena of fluorescence. So in excited singlet state, if the coming back of electron is taking place from the excited singlet state to the ground state, then we will be calling it as fluorescence. And particularly the electron, when it is present in excited orbital, it is having the opposite spin with respect to that second electron that is present in the ground state orbital. Therefore, the total spin value for this system comes out to be plus 1 by 2 and minus 1 by 2 due to opposite sign. So total spin value is 0. So if we calculate multiplicity m 2s plus 1, so it is coming out to be 2 into 0 plus 1, that means 1. So that's why we call it as singlet state. So as a result of returning of the electron to the ground state, so since it is spin allowed, therefore this type of emission takes place quite rapidly, and therefore the lifetimes are of the order of 1 nanosecond to 10 nanoseconds, you can say. So next introductory part that I am covering is that we have to take care for all these phenomena that happens whenever certain part of light is absorbed by a molecule. So when a molecule absorbs light, then simply what happens? Electrons, they will be promoted to higher excited state. So depending on the amount of light absorbed, generally singlet state excitation takes place, but this is not limited to singlet state excitation. Sometimes you can observe that triplet state is also achieved. So this excited state electron can come back to this ground state. So this depopulation takes place in several ways. So we have excited state electron, it has to come back to the ground state. So this coming back to the ground state can happen in a variety of ways. If the molecule is losing its energy in a non-radiative way, correct? So we will be calling it as energy transfer. So this can happen due to collisions with other species. So this is your excited state molecule, and after having collision with other molecule, this energy transfer takes place and it comes back to the ground state. But this route followed by the molecule is non-radiative in nature. Non-radiative in nature, but our focus is on this radiative part. So sometimes what happens if this excited state triplet having some extent of overlapping with excited state singlet. So this is your excited state singlet, this is your excited state triplet. So in case these are having some extent of overlapping, then intersystem crossing can occur. So intersystem crossing can occur. So the molecule has to jump to this triplet state, and from this triplet state, it has to come back to the ground state through this radiative way. And from triplet to ground state, this phenomena we are calling as phosphorescence. So this is not fluorescence. So this is known as intersystem crossing. And sometimes what happens, molecule can partially dissipate its energy by undergoing some conformational changes and relax to the lowest vibrational level. So lowest vibrational level, if molecule is achieving as a result of conformational changes, so then we will be calling it as vibrational relaxation process. So once the molecule is vibrationally relaxed, then the electron is present in the excited singlet state, first excited singlet state to be more specific. And if the molecule that is present in the first excited singlet state, if the electron comes back to the ground state, then we will be calling it as the phenomena of fluorescence, that is for our interest. So all these routes we can depict with the help of this Jablonski diagram. So this is your ground state. This is your first excited singlet state. This is your second excited singlet state. Depending upon the amount of energy absorbed by your molecule, the electrons can jump to this first excited singlet state as well as second excited singlet state. And if the molecule enters into this second excited singlet state, then it can come back to this first excited singlet state through this internal conversion process. And through this internal conversion process, if the molecule comes out to these higher vibrational levels, then initially they have to come back to this lowest vibration level for this S1. So this lowest vibrational level for this S1, if the electron is here and coming back to this ground state, then this phenomena is known as fluorescence. And if overlapping of this singlet to triplet states happens, then some extent molecule can jump to this triplet state with the help of this intersystem crossing phenomena. And from triplet, it is coming back to the ground state. We are calling it as phosphorescence. So audiences, our main focus is in this phenomena, means electron has to jump from this excited singlet state to this ground state. So now some basic questions we have to answer. Why we are interested in this fluorescence spectroscopy techniques. So in order to answer, I will discuss some examples, and with the help of these examples, it will be very clear why this technique is quite important. So some of you might question that if absorption spectroscopy is there, then what is the need for this fluorescence emission spectroscopy? If we do a comparison of absorbance spectra with emission spectra or fluorescence emission spectra, then in absorption spectra, what happens? Due to its instantaneous nature, means if you are providing light to a molecule, then instantaneously the molecule has to enter into the excited state. And the order of time required for this event, generally 10 to the power minus 15 seconds. So you please note down 10 to the power minus 15 seconds or less than that time is required for absorption phenomena. So this time required for absorption is too small that the absorption spectra we are obtaining, these are non-sensitive to the molecular dynamics, because molecular dynamics requires more time. But this absorption is happening of the order of 10 to the minus 15 seconds. So in case our interest is to study the molecular dynamics, then this absorption spectroscopy is not going to fulfill the purpose. Now, what happens in case of emission spectra? In contrast to absorption, emission phenomena takes place. How much time it needed? 1 nanosecond to 10 nanosecond, means 10 to the power minus 9 seconds time is required for this phenomena. And here how much time it was requiring? 10 to the power minus 15. So 10 to the power minus 9 seconds, it is quite large time interval. Therefore, the length of this time, if fluorophore spent in the excited state or if fluorescent molecule remains in the excited state, so this length of time is providing us an opportunity for interactions with other molecules in the solution. So therefore, this emission spectra, this is quite sensitive in nature due to its longer lifetime values. For example, I am going to demonstrate this concept with the help of these two graphs. So simply you need not to know what is happening. So just focus on these two bands. This band corresponds to neutral species. This band corresponds to anionic species. So if we monitor the absorbance spectra for this system, so here we have dissolved this 2-naphthol in water and certain weight percent of ionic liquids are there. So absorbance spectra is showing what? Neutral species is also present, anionic species is also present. Correct? But when we monitor the fluorescence emission spectra, so fluorescence emission spectra, this band corresponds to neutral, but we are not having this anionic band. Where does this anion is going? So absorbance spectra is showing presence of anion as well as neutral, whereas fluorescence emission spectra is indicating that only neutral species are there in the solution. So where does this band goes? It means that what is happening in the ground state, something extra is happening in the excited state, as a result of which this band is disappearing. So the same type of behavior we obtain for this system as well as for this system. But for this system, we are having fluorescence emission from both of the things. So this is, I'm not going into the details because all these things are research related. So one thing I have made it very clear that there are certain phenomena that happens only in the excited state, and in case you are planning to monitor those phenomena, definitely you have to rely on the fluorescence measurements, because absorbance measurement, these are not going to give you the exact information about your system. More importantly, in case you are interested in the study of ground state behavior of your system, definitely go for absorbance spectra. And in case you are interested in learning what is happening to your system in the excited state, definitely you have to collect the fluorescence emission spectra. So I think now I am clear. So pictorially we have depicted the formation of this non-emissive complex in the excited state. No such formation of non-emissive complex was taking place in ground state. So in one case this is happening, in another case this is not happening, therefore we are having emission from. So this is something that is published part of my work. Now coming back to this basic measurements of this fluorescence. So in case your system requires the measurement of fluorescence, so what you have to do, you should have a light source, then excitation monochromator. Purpose of this excitation monochromator is that we have to excite our samples at a particular wavelength. So this light source, it gives light of all wavelength, but for excitation we have to select a particular wavelength. Why we have to select a particular wavelength? Going back, so if this is the neutral species, you want to monitor the fluorescence emission from this neutral species, then you have to excite this neutral species with a light that is suitable to this. How this suitability is to be checked? So corresponding to this neutral band, so it is around 330 nanometer. So this neutral species requires 330 nanometer excitation. If you want to monitor this anion, so for this anion, this suitable wavelength for excitation will be around 365 nanometer. So therefore, experimental setup is to be done in such a way that after having this light from the source, you have to excite your sample at certain wavelengths. That depends on the nature of your absorbance spectra. So from absorbance spectra, select those wavelengths which are going to serve the purpose and set your excitation monochromator at that wavelength, do excitation. So here this is cubate and your sample is there, and some solvent is also there, and your probe molecule means the fluorescent molecule whose fluorescence you are going to monitor. So you are exciting it. After excitation, you have to collect the emission. So emission spectra, sometimes it is also needed. Therefore, emission monochromator is also there. And this is to be detected with the help of detector. So two type of study we can perform using steady state fluorescence spectroscopy. One is known as emission spectrum. So emission spectrum can be acquired by keeping this excitation wavelength as constant. So you are fixing the excitation wavelength, correct? And this fluorescence intensity you are measuring as a function of wavelength. You are measuring this fluorescence intensity that is coming out at different values of the wavelength. And in case your interest is to find out the excitation spectrum, then for excitation spectrum, so you have to measure the fluorescence intensity at a particular fixed wavelength at which your molecule is supposed to emit. So for this, you have to vary your excitation wavelength. So therefore, excitation monochromator as well as emission monochromator both are generally inbuilt with the instrument. For an ideal spectrophotometer, ideal spectrofluorometer, so certain conditions they should fulfill. This is about your light source. So what it says that light source must yield a constant photon output at all. So this light source, it should not distinguish the wavelengths. It should emit all wavelengths with same constant photon output. So second is related to monochromator. So you have to choose your monochromator in such a way that it has to pass all wavelengths, photons with equal efficiency. It should not be selective. I will pass only 375 nanometer more preferentially as compared to 340 nanometer. No. It has to pass all the photons with different wavelengths with equal efficiency. So graphically we can show this efficiency should be same throughout the wavelength range. Next is monochromator efficiency must be independent of these polarization effects. And fourth one is the detector that is generally photomultiplier tube. So it must detect photons of all the wavelengths with equal efficiency. So these are some characteristic features for an ideal spectrofluorometer. So you have to take care for all these things. So schematic diagram for this instrument is that we have a light source, that is tungsten filament is there, 450 watt, 70 watt, 75 watt. So this source is there. So from this source we are having light of all these wavelengths. Then excitation monochromator is there. Purpose of this monochromator I have already explained. So out of all these wavelengths that are emitted by this light source, only one particular wavelength will be allowed to enter into this compartment. So this is your sample compartment where this lid you can open and you can fit your cubate having your sample inside this and close it. And then this is emission monochromator and here it is detector. So this L-shaped geometry, this is generally preferred for measurement of this fluorescence phenomena. So this is what is happening inside in the instrument. These are the ray diagrams. You have light source, xenon arc lamp is there. So dual grating excitation monochromator so as to monochromatize light. Then one shutter is there. Purpose of this shutter is there. So you have to program this. This shutter will open whenever your instrument is ready to collect readings. And then beam splitter is there. One part of this beam goes to your sample, another part of this beam directly goes to your photomultiplier tube, PMT. So this is your sample compartment where you have to put your sample. So beam is coming in that direction and fluorescence is being measured in that direction. So this 90-degree geometry we have to maintain again. So these are some experimental setups in order to collect this fluorescence emission. What you have to do, you should have some starting skin wavelength, you should have some end skinning wavelength, you should have some excitation wavelength. Suppose your molecule wants to have 350 nanometer light for absorbance. So simply you have to provide this 350 for excitation and you have to start your emission collection 350 plus 10 minimum. So from 360 you can collect, and 350 times 2 means 700 minus 10. You can go only up to 690. So that depends on the spectrum of a particular fluorophore, in which range it is emitting. So you have to fix these wavelengths depending on the spectrum, and you have to select this wavelength depending on the choice of the molecule, because molecule have a choice to select wavelengths at 350 nanometers. So this is experimental setup, or the program you have to fix before acquiring. Then this one corresponds to your emission spectrum. This one corresponds to your excitation spectrum. So in excitation spectrum, we have to fix emission wavelength, but here we have fixed what? Excitation wavelength. Then you have to start your skin range from this 220 to 360, and these increments values means after every 0.5 nanometer, it has to collect the readings. It has to collect the intensity. And how much time is required for one reading? So 0.1 nanoseconds, these are the values, you can change these. So these are something related to the programming, how you have to program your experiment. So in case you have some solid samples, so this is SS3 for solid sample, and we are calling it as solid sample holder. Now, how to report the results? So while measuring the fluorescence emission spectra, we have wavelength skin, then certain wavelengths are there, and corresponding to these wavelengths, we are having fluorescence intensity. So we generally report fluorescence emission spectra as a graph of emission wavelength versus relative fluorescence intensity. So this graph, we are exciting the same sample at different wavelengths. So at 320 nanometer, 340 nanometer, these excitation wavelengths we have changed, and emission spectra is also changing. And this is nothing but we have just normalized our plots. So fluorescence spectra, these are presented as emission spectra, and fluorescence emission spectra, this is nothing but it is a plot of fluorescence intensity is plotted against emission wavelength, and this wavelength is reported either in terms of nanometer or in terms of wave number. Now coming back to some characteristics of fluorescence emission. So most of the time you will feel that there is something that we call it as stock shift. So I am going to discuss what is the meaning of this stock shift in case of fluorescence spectra. And emission spectra, these are generally typical independent of the excitation wavelength. So sometimes they can be excitation wavelength independent, sometimes they can be excitation wavelength dependent. That depends on the nature of your system. And certain exceptions to mirror image rules, they can be observed. So coming back to this stock shift. So this stock shift is nothing but the wavelength at which you excite your sample and the wavelength at which they emit. These two wavelengths differ from each other, and the difference between these two wavelengths is known as stock shift. So we call it as that energy of this emission that is typically less than the energy of the absorption. Means whatsoever amount of energy is absorbed by your molecule, by your system. So suppose this is the amount of energy absorbed, and how much amount of energy will be emitted? Only that much amount of energy will be emitted during fluorescence. So this is excessive amount of energy. This excessive amount of energy that have been absorbed by your molecule while jumping to this second excited singlet state. So this will disappear in the emission spectra. Therefore, stock shift generally takes place. And fluorescence typically occurs at lower energy values or longer wavelengths. Next is this Casa's rule. It says that same fluorescence emission is generally observed irrespective of the excitation wavelength. So why it happens? Because you have to excite, suppose larger amount of energy is absorbed by the molecule, and before showing fluorescence, it has to come back to the lowest vibrational level of the first excited state. It has to come back. And from this lowest vibrational level of this first excited state, the fluorescence phenomena has to happen. So whatsoever high amount of energy you are supplying, we are not taking for that. So our interest in fluorescence is only from this lowest vibrational level of this first excited singlet state to that much. So therefore, the same fluorescence emission spectrum is observed irrespective of the excitation wavelength. You excite with different wavelengths, simply provide different amount of energy to your fluorophore, but initially it has to come back. And once it has come back to this ground state, lowest vibration level of this first excited state, then only then it is allowed to show fluorescence. Therefore, but some exceptions are also there. It is not always true, but for maximum cases, you will observe that same fluorescence emission spectrum is observed irrespective of the excitation wavelength. So some other important facts are that whenever the fluorophore return to the ground state, then it can return to any of the ground state vibration level. So coming back, these are the different vibration level. Your fluorophore can return to any of the vibration level. It can return to this lowest vibration level of this ground state, first vibration level, second vibration level. So it can return to any of the. So is everything is going smoothly?
Yes, sir.
Yes,
Okay.
sir.
Thank you. So this is also interesting. And another important thing is that if we think about the spacing of vibrational and energy levels, these spacings that are in between different vibrational levels. So the spacing of vibrational energy levels of the excited state as well as ground state both are same. And consequences of above the two facts. Generally, it happens that emission spectrum are typically a mirror image of the absorption spectrum of the S0 to S1 transition. If we are thinking about S0 to S1 transitions, then what is happening in the excitation spectra? Same thing you will observe in the emission spectra. For example, this one is the emission spectra for anthracene, this one is the excitation spectra for anthracene, and both you can say one is nothing but it is the mirror image of each other. Next, it comes to fluorescence polarization or anisotropy. Sometimes we have to perform these polarization-based studies that we are calling as fluorescence anisotropy. So anisotropy measurement, they can provide information related to size and shapes of proteins in case your work is related to proteins. And in case you want to study the rigidity of the various molecular environment, then these type of measurements you can perform. So anisotropy measurements, these can be used to study the protein-protein association, fluidity of these membranes, and in case you are performing some immunoassays of numerous substances, then you can do this fluorescence anisotropy measurements. So fluorescence anisotropy measurements are based on the principle that if you are doing the photoselective excitation of the fluorophore by a polarized light, photoselective excitation means, we will discuss later on, please keep this term in mind. You are doing photoselective excitation of the fluorophore by a polarized light. So initially we were doing excitation with non-polarized light, but here we are doing the excitation with the help of a plain polarized light. Then what will happen in case you are using a plain polarized light? Then your fluorophore, it will absorb certain selected photons and it will show some preferences, and preference will be in such a way that it will absorb only those photons whose electric vectors are aligned parallel to the transition movement of your fluorophore. So the transition moments for a fluorophore has certain well-defined orientation with respect to the molecular axis. For different molecules, it has different alignments. So this is the way it happens. Suppose you have randomized fluorophore like this, these are your randomized fluorophore, then your emission will also be randomized. Unpolarized emission will be there, correct? But in case you are using a plain polarized light, then this plain polarized light, definitely it will excite only certain fluorophore whose orientation is favorable with this plain polarized excitation. So out of all fluorophore present here, some will be excited. So therefore, the emission that will be collected for this system, it will also be polarized in nature. Correct? So if rotational diffusion is happening for this system, you have done photo-selected excitation, but due to rotational diffusion, what will happen? This system will turns out to be this. So interestingly, what will happen? Do polarized excitation. If you are having polarized emission, it means that very less rotational diffusion is there. But you are polarizing your fluorophore and you are having unpolarized emission, it means that something is happening. As a result of which your polarized or photo-selected fluorophores, they are converting into the randomized fluorophore. And why this is happening? This is happening due to rotational diffusion. So I think to monitor this rotational diffusion, this anisotropy measurements, these are going to give you the value, correct? So mathematically, we have to calculate these anisotropy values, and fluorescence anisotropy R that we are going to define. R is nothing but I parallel minus I perpendicular divided by R I parallel plus twice of I perpendicular. These are the intensities for perpendicularly and parallelly polarized lights emissions. So here this I parallel and I perpendicular, these are fluorescence intensities for these vertically and horizontally polarized emissions. So once you have to excite your samples with vertically polarized light, once you have to excite your samples with horizontally polarized light, you have to find out the intensities and then you have to calculate the value of the anisotropy. You can do the measurement of polarization by making use of this formula, I parallel minus I perpendicular divided by I parallel plus I perpendicular. Just a moment, please. Next is it comes to fluorescence quenching. Sometimes what happens? Fluorescence quenching takes place for your samples, and fluorescence quenching, it is nothing but it is any process as a result of which there is a decrease in the fluorescence intensity values. If some decrease in the fluorescence intensity values is happening, then we can call it as that quenching phenomena is happening. So this quenching can be associated with a number of molecular phenomena that are happening. Sometimes some excited state reactions takes place, sometimes some molecular rearrangements are taking place, sometimes some energy transfer or ground state complex formation, or sometimes as a result of collision between other molecules, this quenching phenomena can happen. So this quenching phenomena is reported in terms of Stern-Warmer plot. So F naught by F is equal to 1 plus KSV times Q. Q is your quencher concentration. F is your fluorescence intensity in presence of quencher, and this F naught is fluorescence intensity for your fluorophore in the absence of any quencher. And if your system is following this Stern-Warmer plot, then for this system we are having this concentration of quencher, and this concentration, this F naught by F, straight line will be obtained, and the intercept of this will be calculated. This y equal to mx plus c. So this 1 will be the intercept on this y-axis. If your graph is like that, your system is following this Stern-Warmer plot. So sometimes this plot is not straight line. Some deviations also takes place. So in case both static as well as dynamic type of quenching is happening in your system simultaneously, then we can observe these type of things. So non-linear plots can also occur in case of purely collisional quenching if some of the fluorophore are less accessible as compared to the other fluorophores. Next, it comes to quantum yield. So in order to measure quantum yield, you have to measure the number of photons that are emitted to the number of photons that are absorbed. So while excitation, you have to provide certain photons, and these photons are absorbed by your fluorophore. And while coming back to ground state, some photons are to be emitted. So quantum yield is nothing but it is the ratio of the number of photons emitted to the number of photons absorbed. So mathematically, this is nothing but it is ratio of rate of radiative decay divided by rate of radiative plus non-radiative decay. So some quantum yield standards, we make use of quantum yield determination, and easiest way is to estimate the quantum yield for a fluorophore by comparison with the standards of non-quantum yield. So for standards, the values of quantum yield are mostly independent of excitation wavelength. So these standards can be used wherever there is a useful observation. So all you please wait for a moment. I am joining within 2 minutes. Please.
No issues, sir.
So coming back to our discussion, that once you measure these quantum yield values, how you can interpret these? So quantum yield values are nothing but these are an estimation how strongly your molecule is showing fluorescence. So higher values correspond that your molecule is strongly fluorescent in nature. So for quantum yield value determination, we have to take care for these optical densities values. Generally, these are kept below 0.05. Optical density means absorbance value for your samples. It should be less than 0.05. So why we are keeping these? Because we want to avoid these inner filter effects that can cause some problems in the measurements. And determination of these quantum yield is generally accomplished by doing a comparison of the wavelength integrated intensity of our unknown, whose quantum yield is to be measured, with reference or standard. So mathematical formula for calculation of quantum yield values, this is Q. Quantum yield for your unknown is equal to quantum yield for your reference that you have chosen. This I is the intensity for your sample. IR is the integrated intensity for your reference. OD is the optical density for your reference, OD for your sample, and this is a refractive index values for your sample, and these are the refractive index values for your reference. So next I am going to discuss for a moment this inner filter effect. So these effects leads to a decrease in the intensity of the excitation at the point of the observation. So if you are performing excitation, then these excitation values will undergo a decrease, or decrease in the observed fluorescence value will be there. So fluorescence intensities, these are generally proportional to concentration over only limited range of the optical densities. Therefore, in order to avoid from inner filter effects, our sample should be quite dilute in nature. And generally, fluorescence spectroscopy is performed for 1 molar, 1 micromolar, 2 micromolar, up to 10 micromolar dilute solutions only. So this is inner filter effects. The high optical densities are causing a distortion in the emission spectra. So these are the emission values for anthracene for different concentration. If your sample is 10 to the power minus 6 molar, 10 to the power minus 5 molar, 10 to the power minus 4 molar, and 10 to the power minus 3 molar. So some distortion is taking place for these. So consider you are having a 1 by 1 centimeter cuvette and you are illuminating it centrally, and optical density for your sample is 0.1. So if you use the definition of optical density log of I naught by I, you know, this is going to give you the absorbance value. So the light intensity at the center of the cuvette, this will be only 0.88 times of I naught. Means you are losing about 10% of your light intensities. Therefore, if concentration or optical density of our sample is 0.1, then there is a decrease about 10% in the fluorescence intensity. Therefore, we prefer to use very dilute solutions for the measurement of fluorescence. Some effects of sample geometry are also there. I have already explained it that we have to choose this 90-degree alignment in order to monitor the fluorescence emission spectra. And some effects of solvents also takes place on the fluorescence spectra. In case your solvent is showing different polarity, different viscosity, these are going to play an important role on the emission spectra. Rate of solvent relaxation, pro-conformational changes, sometimes the rigidity associated with the local environment, and sometimes if some internal charge transfer process is happening, then these processes, they can lead to different fluorescence emission spectra. So next comes to fluorescence lifetime. So fluorescence lifetime can be monitored with the help of specific time correlated single photon counting techniques. And if meaning this life is concerned, so lifetime, this is nothing but it is the time spent by your fluorophore in the excited state. You have to excite your samples and your fluorophore will remain in the excited state for certain interval of time, suppose 1 nanosecond, 2 nanoseconds, 3 nanoseconds. So how much time it is staying there in the excited state, that we are going to monitor with the help of fluorescence lifetime measurements. So mathematically, this fluorescence lifetime measurement is tau is equal to 1 by this radiative decay rate divided by non-radiative decay rate. Or in case no non-radiative decay is there, then in case of non-radiative decay, we are less intrinsic or natural lifetime values. So now I'm going to answer, if we have measured the steady state fluorescence already, then why we are going to measure this time resolved fluorescence values. So samples that we illuminate during steady state fluorescence emission spectra collection, so we make use of continuous beam of light and the intensity or emission of spectrum is recorded. But in lifetime measurement, the sample is exposed only for a short interval of time with the help of a pulse of light, correct? And generally, the width of this pulse is shorter than the decay time of the sample. And since the time scale of this is of the order of nanoscale, and most of the measurements are steady state in nature. And in case of time resolved emission, what happens? The intensity decay is recorded with a high speed detection system. And with the help of that detection system, you can do the anisotropy measurement, you can do the intensity measurement on a time scale of nanoseconds. So these are the relationship between the steady state and lifetime measurements. One thing I would like to make it very clear that lifetime measurement, these are quite expensive in nature, because the experimental setup that required for lifetime measurement is of the order of a minimum 50 to 60 lakhs you have to spend on this. So precise shape of the anisotropy decay, it contains, in case you have collected the lifetime measurement values, then these shapes of the anisotropy decay appropriately the curve, they can provide you quite information related to your flexibility of the molecule, macromolecules. So in case of steady state measurements, this is not possible. On the other hand, if you have measured the lifetime values for your system, then it can reveal whether this switching that is happening, this is due to the diffusion process or some complex formation or some ground state fluorophore is undergoing any interactions. So all these interesting information you can obtain with the help of light measurement. This is the instrument setup. That is instrument that is supplied by Horiba. So in IIT Delhi, so many instruments are there. So this is select how to control the band pass, how to select the monochromator wavelength dial. Simply you have to rotate it. These wavelength values you can select. These are the decay curves. So you are exciting when your fluorophore is coming back to the ground state and the time interval, how much time it requires while coming back to the ground state. That will be. So time-resolved data generally obtained from the instrument looks like this. And after doing certain analysis, we perform these type of plotting. And these type of plotting, this dot, red dots, these are your decay profile. And one prompt as a reference is also used with almost zero lifetime. So these blue dots correspond to your prompt response. And these are the fitting you have to do, fitting either in single exponential, double exponential, triple exponential. So that depends on the nature of your system for the lifetime measurements. So these are some other data for lifetime values. So this is temperature dependent study, how the lifetime values, they vary when we are changing the values of the temperature. Now it comes to the most important topic of discussion, COVID-19 disease testing utilizing this fluorescence. So in market, several diagnostic methods they have been designed, and one USA FDA approved method test kit that is making use of fluorescence-based reverse transcript real-time polymerase chain reaction. So with the help of these fluorescence techniques, what we are doing, we have to monitor reverse transcript real-time polymerase chain reaction. Correct? So RT-PCR test, this works by detecting the replicated nucleic acid copies from the SARS-CoV-2 virus through a bound fluorophore probe. It means that in the detection of this virus, we are making use of a fluorophore probe. Fluorophore probe means a molecule which is showing fluorescence. And by making use of so many observations, we have to select it. So I will discuss how we are going to select this fluorophore probe molecule. So this fluorophore probe molecule will be released from its quencher counterpart. Quencher counterpart means one quencher is also there in this technique, one fluorophore is also there in. So whenever this fluorophore and quencher both are associated with each other, then no fluorescence will be observed, because the emission that is coming from this fluorophore, that will be absorbed by your quencher. So fluorescence intensity will be quite low. But once this fluorophore is free, when it will be free? Whenever you are COVID positive. So let's see how it works. So we have to take care for fluorescence intensity measurements, basically. So in RT-PCR techniques, we have to make use of these two biomolecules. You can see one is carboxyl fluorescein. This is highly fluorescent. We are calling it as FAM. So this 5,6 carboxyl fluorescein, it is an emitter, means it is a fluorescent molecule. So this is your fluorescent molecule. And this black hole quencher. Quencher, you know, what is the purpose of quencher? Quencher generally quenches the phenomena of fluorescence. So this is quencher. So these two molecules are selected in such a way that the wavelength of emission of this emitter molecule or FAM molecule, it coincides with the absorption of your quencher molecule. So the wavelength emitted will be absorbed immediately by this quencher. Therefore, the fluorescence intensity values will be quite low as soon as both of these molecules they are present in your system or they are close to each other. Correct? Let's see what happens. So this is your FA molecule, this is PHQ molecule. So both are present nearby to each other. So fluorescence quencher probe in solution. So minimal emission will be there because the light emitted by FAM will be absorbed by BHQ. So emission spectra will be quite poor. You do PCR, means you are doing polymerase chain reactions. So this polymerase chain reactions, it requires some time. That's why in the initial days, people were saying that 48 hours are required for PCR testing like that. So all these are quite complex in nature. So whenever polymerase chain reactions happens, then release of this FAM, some part of this FAM becomes free. From TAQ, this P hydrolysis, and whenever this FAM is free, then it starts emitting. Then our instrument start detecting now fluorescence intensity have been increased. So how many polymerase chain reactions are happening? How many polymerase chain reactions are required for detection of this emission from FAM5-? That is going to decide whether you are COVID positive or not. So let's see. So what happens? Initially, this testing starts with extraction and isolation of all RNA from the patient sample. So appropriate specimen is taken from an individual's respiratory systems. You know the respiratory systems, they generally took this specimen. But problem is that your PCR polymerase chain reactions, it does not support with the RNA. Correct? So this is your sample and this is not going to support because your samples, these are having RNA. So what you do the reverse transcription. So the RNA is isolated. So we have done isolation of this RNA here, correct? And once this isolation is over, then reverse transcription is to be done and we are having complementary DNA that we are calling as cDNA. So this RNA is converted to this complementary DNA as a result of this reverse transcriptase, that is an enzyme. So we are taking help of an enzyme, correct? Now, DNA can be amplified. We have this RNA converted to complementary DNA. Now we are doing the amplification of DNA and quantified using a polymerase chain reactions. How many DNA are there? We are doing quantification of these with the help of polymerase chain reaction. So complementary DNA, they undergoes PCR test or PCR process to amplify the number of cDNA copies with several sets of these primer and probe detection targets. So let's see what happens. So this is real-time RT-PCR. So this is your fluorescence quencher probe, it becomes free. So when PCR cycle reaches the extension phase, then what will happen? This TAQ polymerase primer nuclease activity, this TAQ polymerase nuclease activity on this 5' of ruptures means it ruptures and FAM from BHQ1 in the probe and its fluorescence is measured. Once it is free, then it starts showing fluorescence. And this fluorescence we are monitoring as a function of each cycle. In one cycle, how much fluorescence intensity we are having? We will increase the number of cycles. This free FM will be available. 1 cycle, 2 cycle, 3 cycle, 5 cycles means concentration of this FM will be increasing in our sample. person. If CT value is 30, still it is positive, but not too much. But if your CT values are 50, you are COVID negative nature. So I think I am clear now. With this, I would once again thanks each and everyone for your kind attention. And I think if any question is there, then this session is open for questioning.
Thank you, Dr. Vinod. Students, if there are any queries or something you wish to know more about the topic, you can just put in your queries in the inbox.
I think the most important information that we have provided today, how RT-PCR test works and how this fluorescence technique is going to help you, and why so much time is required, why this technique is quite expensive. I think all these things are clear to you.
Thank you so much, sir.
Thank you, sir. I would like Dr. Paramji.
Hello, sir. Thank you, ma'am. Participants, have you any queries?
So if any question is there, then the session is open for questions.
Thanks so much, sir. If we have any queries, we can
So I think no question is there. So we should close this session.
Okay. Uh, uh, Thank you so much, sir, for acquainting us and sharing your out. Hello, is I was audible now?
Now it's fine.
Yeah. Okay. I would request Dr. Anshul. Thank you so much, sir, for
Good afternoon to all.
having us today. Thank you so much, sir, for today with